Okay, welcome everybody. So in this video, I am hoping to talk to you about calorimetry and also about the first law of thermodynamics and what enthalpy is. So let's start with the law of conservation of energy. And what the law of conservation of energy says is that energy cannot be created or destroyed. It can only be transferred. Between two objects. It can also transfer form, so kinetic to potential, chemical to heat, those types of changes. So another way of looking at the conservation of energy is that the change in energy of the universe is equal to 0. And what this means is that the change in energy of the system is equal to the opposite energy change of the surroundings. And this is because the change in energy of the system plus the change in energy of the surroundings is equal to the change in energy of the universe. The idea is that if the change in energy of the universe is 0, and I have these terms equal to 0, I can then set them equal to each other, have one positive, have one negative. Now we talked briefly in class about measuring different energy units, and if you're a history buff and you took a look at that article talking about the history of the discovery of energy and the sort of history of thermodynamics in general, hopefully that gave you some insight. But the energy, we're going to mostly use joules. Sometimes we'll use calories. And so just to reiterate this, a joule is equal to the amount of work that is done, and it could be heat as well. But if we look at the units of work, we have a force times a distance. And if we break down a force, we have a mass times an acceleration times a distance. And if we start plugging in units, we would have kilograms times meters over seconds squared times a new distance meters. And together, this would give us kilograms times meters squared over seconds squared. And this is what a joule is. A joule is equal to a kilogram times a meter squared over a second squared. We can also use calories, and there's 4.18 joules for every 1 calorie. It's going to become important if we're doing conversions between the two. Now energy is something called a state function. And what a state function is defined as, it is a property that depends only on the current state of the system. So take, for example, you walk into a room and there is this 50 grams of water sitting in a beaker at 25 degrees Celsius. And I ask you, how did it get there? And so one of you says, hey, that 50 grams started off as water that was boiling, and over time it cooled down, and now it became 50 grams of water at 25 degrees Celsius. And somebody else says, no, not at all. It started off as ice water, or maybe even total ice. Here we have solid ice. And it just, we heated it, and eventually it reached this point. The fact that it doesn't matter how it got to the 25 degrees Celsius makes this a state function. Energy is a state function, because energy, it could be a whole mix of different things. Remember, the change of energy is equal to Q plus W. So when I say a mix of different situations, it could be all heat, it could be all work, it could be a combination of the two. Because that change in energy doesn't depend on, how it happened, that means that it is a state function. Now, we're going to talk a lot about enthalpy, and when we look at a chemical reaction, enthalpy, and you've heard this term before, generally we mean that it is just heat. But in a reality of the situation, if I were to, solve for heat, I would have, remember, change in energy equals Q plus W. If I substitute in here delta H for Q, and I solve for it, I get this equation over here. So the change in heat, which is enthalpy, is actually equal to the change in energy plus the work that's done. Now, I have work here as P times change in volume, and that's because work is equal to a force times a distance, which has the units of pressure times change in volume. We saw this in one of the practice problems that we did in class. Now, the thing is that when we have a system in chemistry, the work part here is extremely small. It's very, very small. And most of the energy is just lost as heat. And so we can simplify this. And we can simplify it as change in heat is equal to the change in energy. I like to say that in chemistry we do no work, and I mean it, because really it's all about this heat release. We're not doing much useful work in terms of an energy change. We're doing a heat release. Now, from now on, we'll talk about delta H, we'll talk about enthalpy, and we'll understand it as a change in heat being released with no useful work being done. The two types of changes in energy or enthalpy that you can have is either endothermic and exothermic. And I feel like you have a really good idea of what these mean, but just to put it in terms here of enthalpy and remind you, you have a negative change in heat for exothermic, and you have a positive change in heat for endothermic. You might remember these graphs, which we'll do again later on in the year, but just to bring them up here, you have these potential energy diagrams where you have this delta H value. This is potential energy, this is time. Notice that this delta H, the products minus the reactants, is negative. And so the change in enthalpy of the products minus the change in enthalpy of the reactants will give you the change in heat of your reaction. And in this case, if we were to assign numbers, let's say that this was 20 and this was 50, we would have 20 minus 50, and we would have a negative 30 value. And that would mean that we're releasing heat. This is always in the case of the system. So since we observe the law of conservation of energy, the change in heat of the system is going to be equal to the opposite change in heat of the surroundings. Endothermic is going to look all the opposite of this. We're going to have our graph where we're going to start low and end high. We're going to have reactants and products, potential energy, time, and now if we assign those numbers here, 20 and 50, we would have, again, we just take this and paste it over here, we would have our same setup, except now we would have 50 minus 20, and this would be equal to a positive 30. The positive delta H of the system is equal to the negative delta H of the surroundings. Now, there are different changes of reaction. The most general kind is, and this goes for pretty much anything, delta H reaction. RXN means reaction. But we could also have a delta H where we have specific reactions like combustion. This would be for a change like if you had CH4 plus oxygen yields CO2 plus H2O. These are always negative because the heat of combustion is always releasing heat. You could also have something called delta HF naught. And this is the heat of formation. And the heat of formation, you need to know the definition for this one. It is the heat change. It is the heat change when 1 mole of a compound forms from its elements. So what does that look like? Well, let's take a compound and form it from its elements. Let's take hydrogen plus oxygen and form water. Now, in order to be a heat of formation, it has to be, and this is really important, 1 mole of the substance. So that means that I need a fractional coefficient in front of the O2. This will have the units of kilojoules per mole, because it's always per 1 mole. Heat of formation is only valid if it is for 1 mole of a compound forming from its elements. Lastly, you could have something like a delta H of solution. And this is when a compound dissolves in water. And so we could have something like, NaOH, solid, dissolving in water and forming Na plus and OH minus aqueous. This usually has the dimensions of kilojoules per mole. So where does all these, different heats of reactions come from? Well, there are different things to consider, and they don't really test very much on this, but I just put this in and you can look it over. The kinetic energy contributions are like how the molecules are moving, they're rotating, they're vibrating, they're, like the electrons are moving. These happen to actually be a very small part of it. The delta H can, the big changes come from when you have potential energy contributions, like forces between the atoms, forces between the nucleus and the electrons, forces between the nuclei and the shared electrons in each bond, and that one is by far really the big one. That one blows everything else out of the water. That's where the major contribution comes from. Now, how do we measure these heat changes? And this is what I really wanted to get to in this video. And we do it using something called calorimetry. And the device that we use is the calorimeter. The calorimeter is a specialized device, and it allows you to measure the temperature change in a chemical or physical change. Now, the two types are a bomb calorimeter over here on the left, or a coffee cup calorimeter over here. I feel like most of you have experience with the coffee cup calorimeters, whereas very few of you have experience, or none of you really have experience with a bomb calorimeter. The bomb calorimeter, the math is a little bit different than the coffee cup calorimeter. But looking at the bomb calorimeter and just going over some of the details, I'm highlighting here in green, hopefully you can see it, maybe I should pick a different color here, highlighting in red here, the bomb chamber. And that bomb chamber is where the chemical reaction takes place. So the chemical reaction takes place in that bomb chamber. It gives off heat. It's a combustion reaction. That combustion reaction gives off heat, and that will heat up the water around it. So there is going to be a change in temperature, a delta T of the water. The math for this is that the change in heat, which is called Q, is equal to the change in temperature times the calorimeter's constant, which is the heat capacity of the calorimeter. This is not specific heat. But specific heat of water plays a role in that value, and you'll see why. We'll do a calculation with the bomb calorimeter on the next slide. And the other one is a coffee cup calorimeter over here. And this one we're really going to use Q equals mc delta T. Notice for the bomb calorimeter, nobody really cares about the mass because the mass part is baked into this value right here, and you'll see why in a second. The coffee cup calorimeter, people can manipulate the mass. They can put different amounts of water in the coffee cup calorimeter. Normally with the coffee cup calorimeter, you fill this with water, and then you do a reaction within the water. You dissolve a solid perhaps, or maybe you would neutralize an acid and a base, or maybe you would put a hot piece of metal in there and transfer the heat that way. But that's what's happening with a coffee cup calorimeter. So let's try a few different problems here for this. Let's try one with a bomb calorimeter. And so let me pull one up here on the side, and we can talk about that one. And so the problem looks like this, okay? What they say is that you have a 1 gram sample of octane. And this is C8H18 for those of you that don't know. So you have a 1 gram sample of octane. And you're going to put this in a bomb calorimeter that has 1,200 grams of water. And what's going to happen is the temperature, it's going to change from 25 degrees Celsius to 33.20 degrees Celsius. Now, what they tell you is that the calorimeter, the empty calorimeter, with no water in it, has a C of cal empty equal to 837 joules per degree Celsius. And then you have the specific heat of water as 4.18 joules per gram degree Celsius. So the question is going to ask you, calculate the delta H of combustion of octane in kilojoules per mole. So if you want, pause the video for a minute, see if you can do this one. It's hard and we've never done anything like this. Actually, it's not that hard, but we've just never done anything like it. I'm going to pull up my calculator now. If you've come back, if you pause the video, if you tried it, or if not, you're just listening to me. The first thing I need to do is I need to figure out, well, what's the Q total? Well, the Q total is equal to the change in temperature times the specific, the heat capacity of the calorimeter total. Now, this can be broken down further. So the Q total is equal to the delta T, which we know is 33.20 minus 25, that's 8.2. But now I have to deal with the heat capacity of the calorimeter. The heat capacity of the calorimeter total is the heat capacity of the calorimeter empty plus the specific heat of the water times the mass of the water. So what does that look like over here? Well, that would be equal to 837, that's the calorimeter empty, plus the specific heat of the water. Remember, the calorimeter constant is joules per degree Celsius. The specific heat of water is 4.18 joules per gram degree Celsius times the mass of water, times 1,200 grams. So look at what happens to my units here. My grams will cross out with my grams. And now I can do all my math together. So if I go ahead and I do all my math together, I do 4.18 times 1,200. That combines my water and gets me the water component, plus 837. So I get a total of 5,853 joules times degrees Celsius, or divided by degrees Celsius, times 8.2 degrees Celsius. So let's times this by 8.2. We'll get 47,995. And that is now in just joules. Now remember, what the question was asking me for, is, and I'll highlight this, the heat of combustion of octane in kilojoules per mole. So now it's just a matter of, well, let's figure out what we have here. We have our 47,995 joules. Well, let's change that to kilojoules, times 1 kilojoule for every 1,000 joules. The thing also is that this was really per 1 gram of octane, because they told me, if we scroll up a second here, 1 gram sample of octane. But they want it per mole, so times, for octane, that's 12 times 8 plus 18, I think it's like 114, yep, times 114 grams for every 1 mole. And when I do this, if I do my 114 times my 47.995, because I changed that to kilojoules, I'm going to get approximately 5,471 kilojoules per mole. Something that's really important here, and that you should be aware of, is that the sign is negative, because this is a combustion, and in a bomb calorimeter, the change is always negative. Some people like, so that they don't forget this, they like to put a negative sign right up here and just include it in there. So that's one type of calorimetry problem. I have a worksheet on bomb calorimetry that I'll upload that we can try in class. And then the other type of calorimetry problem is when you have a coffee cup calorimeter. And the two types that we have, one is where you just have two substances and they are combined. So like you could have 80 grams of, copper, which has a specific heat of 0.385 joules per gram degrees Celsius at 100 degrees Celsius, and that is placed in, let's say, 500 grams of H2O at 20 degrees Celsius. And the question would be like, what is the T final? So try this one. Some of you, or most of you, should remember how to do it, and we'll go over this one in class. And then the other one that you may see is when you dissolve a salt in water. So let's say that I were to take 10 grams of KNO3 in 100 grams of water. I dissolve that in the water, and I get a temperature change from, let's say, 23 degrees Celsius to 18 degrees Celsius. And the question will ask you, assuming the specific heat of the mixture is equal to 4.18, determine the delta H in kilojoules per mole of KNO3 dissolving. So these two problems, they are the type that you see in a coffee cup calorimeter. So I'd like you to try both these. I'm going to stop the video here. We have lots of time in class tomorrow. We have a double period. We're going to spend a lot of time going through how to do these and working on them together. All right, thanks so much.